next presenter is Bunnie, an American researcher and hacker with a doctorate from MIT. I didn't know this until just the other day, a book that I actually remember reading quite extensively, Hacking the Xbox. And he is a mentor and advisor, and I recently released a very interesting cryptographic wallet, RISC-V. Actually, you may want to very briefly in your presentation say a tiny bit about it. I know we have talked about it in other Silicon salons, but not everybody here was at those. Bunnie, go ahead.
Okay, can you hear me? Let me see, share my screen. All right, can you see it? Should say reflection.
Yes, it is.
Okay, yeah, sure. So I'm Bunnie, and as Chris was saying, I have made a device called Precursor, which is an FPGA-based device meant for security. The idea behind it is that we wanted to kind of go towards how far can you go in terms of trusting your hardware, particularly in the face of supply chain challenges, verifiability, these types of things. So FPGAs are great because you can compile your design from source, so you can know your CPU doesn't have any backdoors on the inside. You can inspect the RTL. And then when you compile it yourself, we do a little randomization trick to make sure that the cells all end up in slightly different locations to the compiler. And so you would have your own unique bit stream. So even if someone had, backdoored a few of the cells inside the FPGA, it's probably not going to be effective. You have to backdoor a lot of them, in which case you would definitely see an impact in the, the power and the size of the chip itself, which is detectable through things like X-rays, much easier means to detect. And so, on top of this, of course, the whole thing is RISC-V based, and it's not just a hardware exercise. We've actually done the whole stack. So we've written our own OS. We've written I think someone's whistling. I think if someone can mute their whistling, please. Yeah. Yep. No worries. Right, and so we wrote our own OS. So we have a microkernel OS that's written in Rust from the ground up, meant to run sort of secure cryptographic applications, can deal with a number of different protocols all the way up to the application layer. And so now we have the device itself can be used as a U2F token, FIDO token, can keep your plain text passwords, keep TOT, HOTP, can connect to Matrix and chat. We have a Wi-Fi connection on it, these types of things. So it's the ecosystem starting to evolve around it and really start to flesh out. So back to sort of where this presentation comes from. So after we put in all this effort to build, this ecosystem on RISC-V, and we're thinking about sort of, security and trust and all sort of stuff, Cranium, as Joe had mentioned, is building an SE, and they want to go for an open approach. And I'm helping, full disclosure, I'm helping advise them on sort of some of the open source aspects of this. In particular, the original draft of the chip had just a Cortex M7 on there, which is an ARM CPU. And we really, from a standpoint of trust and being able to sort of know the really important things are working right, having a proprietary CPU core from ARM that you can't inspect, can't know on the inside seems problematic. And so we're going to try and graft in this RISC-V core that we have and integrate it into their chip. And hopefully with that, we actually can get software compatibility with all of the sort of the existing RISC-V developments around secure wallets and secure hardware. And so this has led to a question, which is like, we're doing all this free open source design, but then when we're targeting the Cranium process, it's on a closed PDK, 22 nanometer TSMC silicon. We can't show you the transistors. We're not allowed. It's under NDA. And so a question that's been sort of dogging me by a bunch of people who have been following my work is that, if you can't trust transistors, why bother with anything else? And so it's, this presentation kind of doesn't fit in with the exact theme of this commons, but Christopher wanted me to sort of talk about it anyways, so here we are. I'll go through it pretty quickly. The basis is that, you care about security and you want to trust your hardware. So, we all know Kirchhoff's principle. We want to avoid security through obscurity. So let's open all the things. Let's have open protocols and applications, have an open kernel, open firmware and bootloaders. These are all kind of no-brainers now. We should have our circuit boards open so we know what should be in there, what shouldn't be there. We'd like to have our chips open so we know what's inside the chips itself. We need to know what the RTL is in a chip. We want to know, what the transistors are supposed to look like. Okay, well now what's making the transistors? We should know something about the masks. What about the chip fabs? The problem is that you can kind of keep going down and down and down and down until you get, to the nth turtle in the row, right? And the concern, the reason why people get really worried about this is there's a worry that, like, what if we're trapped in a simulation, right? If your BIOS is rooted, doesn't matter that your kernel is trusted, right? If your motherboard has a JTAG implant, doesn't matter that your BIOS is signed. If your CPU has patched microcode, doesn't matter that your motherboard is trusted. If your CPU microcode is signed, doesn't matter if you have signatures, if the chip design itself is backdoor, right? Basically you can always walk around any security countermeasure by going one level deeper and then sort of trapping the upper security level into a state where you're like, yeah, no, everything's secure, but actually you're running a simulation and we have this insecure world on the outside. And we're just showing the things we want to show you on the inside, right? So that's the sort of the root of the paranoia, right? And so, there's been a lot of talk about like sort of open PDKs and trusted fabs and that sort of thing as potential solutions to this. Even in places like European Parliament and US Congress, they talk about security as one of the issues, is why they want to bring the fabs over. The problem is that this diagram here sort of in a very broad level shows what the supply chain might look like. On the left-hand side, you have the chip designers and you have developers and we have the Git cloud and all this sort of stuff. And then from the left to the right, we go from chip design to mass prep to chip fab to IC test and packaging to distributors to PCB assembly. And there's a gray market in the middle, and there's a factory that builds boxes. It goes through customs and then it goes to distributors and couriers and finally to other customers, right? And so the open PDK allows you to put some checks on the left-hand side of this diagram, right? But then it completely ignores all these other potential vectors for swapping out your hardware and doing things to your hardware along the way. So unfortunately, this whole Kirchhoff's principle and sort of opening things all the way down actually doesn't even necessarily address the core problems at the end of the day. And the problem is that in hardware, check designs don't necessarily mean check devices. So this diagram here shows the scenario that we're all familiar with in software, whereas we have the Git cloud. It's a Merkle tree, blockchain thing that, you can't stick something in there, too easily. I mean, it's SHA-1, but fine. And then, you have this, maybe even an untrusted build farm, right? And it goes into a CDN, that's some untrusted cloud. Who cares, right? You download into your disk that you can have a signature you can check, right? And say that this is actually matches what is inside Git, and then people can pull off stuff off Git, and they have auditors who can do reproducible builds, and you can do check things back and forth. And so it actually doesn't matter that that whole thing in the middle, the CDN, this cloud is like totally untrusted, because you can do a check in your own CPU just before you run the code. There's no trust transfer like this for hardware. There's no hash function or digital signature for hardware, at least not yet. I am doing in a separate, it's a separate, completely separate topic of discussion, but I am trying to find ways to add some amount of verifiability to silicon through optical inspection means. Like, it won't be perfect, but it'll be much better than what we are having today. And so then, then people say, okay, fine, I'm worried about vectors and chips. Shall I just inspect all the chips down the transistor? And then I get pointed at this paper oftentimes. They say, yeah, well, there's this, X-ray tychography. There's a wonderful Nature paper. They show 3D, extract of a modern Intel CPU here, done down to the gate layer, and it's non-destructive and all this sort of stuff. The problem is that imaging was done at the building you see on the right-hand side. That donut-shaped building is the light bulb. It's an X-ray source, right? That is able to do the light of the intensity and the wavelength that you need to do this type of thing. And so, first of all, not everyone's going to have one of these in their house. And second of all, if you decide to check the chip, you have to FedEx it to this facility, in which case you now have the courier problem again. You check the chip and now you send it back, someone swaps it out. How do you know? Blah, 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 right? So it's like, again, this doesn't solve the problem either, right? And so, I kind of have bad news for people who want to go all the way down through all the turtles. There's no real silver bullets in hardware security. People who suggest formal verification, actually, there's no essential link between formal verification and security, because the specifications themselves just worry about the correctness, but don't necessarily worry about security. Open source doesn't necessarily mean trustable. You have to check the code. It doesn't matter if it's open if you don't check it. Physical inspection has limits, as I've just discussed. Even if you did inspect, yesterday's inspection doesn't ward off today's evil maid. You have to inspect it and then keep it under lock and key and keep an eye on it the entire time so someone doesn't swap it out. Trusted fabs are meaningless with untrusted couriers. And then, people are like, well, we have auditors. Auditors cost money. We have certifications. The problem is certifications are business. They're not a public service, right? They have their own incentives for doing this type of thing. So there's no sort of like there's no bottom turtle, so to speak, in this stack that we can get to at the end of the day. And so what turns out is hardware security is really, at the end of the day, it's a cost benefit trade-off, right? It's kind of like, sort of fatality rates in automobile accidents, right? So we have these very unsavory metrics of things like, acceptable deaths per million and cost of a life and value of these things that people go through. And we, of course, we want to have the rate of accidents to be zero, but it turns out if we were to do that, the societal impact, the sacrifice of driving everyone at 10 miles per hour so you have no more fatal accidents would not be accepted, right? So you have to have a clear-headed view of sort of like, how much does it cost? And then what you want to, what's acceptable at the end of the day. So the fundamental questions when we're talking about hardware security is like, how much does it cost to break the security? How much do you lose if the security is broken? And accurately assessing that and having a clear-headed view is very fundamental. So the reason why the cost assessment is hard is that it's just human nature to fear things that you don't understand well, things that you have uncertainty about, right? So on this diagram here, there's a list of sort of things from top to bottom of the stack of typical sort of problems you might have that can cause security issues. Like the very top, user error, like, phishing. I typed the password in wrong. I emailed something to the wrong place. I've been phished on a phone call or something like this, right? That's a well-known issue. We all kind of know what it is. Then there's protocol errors, like, TLS, had some protocol bugs and downgrade issues, that sort of stuff. Software bugs underneath that, when people have random number generators and accidentally only take the bottom 16 bits or something like this. Hardware bugs, you have potentially issues when like implementations of AES where you can mutate like 1 byte at a time of a key, which completely breaks the security of the thing in practice. Then you have side channels where, okay, fine, now we can go ahead and put a little voltmeter on a chip and sort of watch it crunch away at RSA and then read out the ones and zeros. And then finally, direct readout, as Joe actually went through in wonderful detail in the previous slide, you can actually just, at the end of the day, read bits off of flash, read them out of SRAM, right? People tend to fear what they don't know as well. And so, when you can't see the mask, you can't see the hardware, and you haven't done it in practice, these boogeymen of sort of side channels and direct read on hardware bugs seem much larger in terms of a thing to worry about than perhaps they really should be. I would probably draw, if we actually drew the diagram where the width of the surface was actually the size of attack surface, I think it probably looks a bit more like this. The actual biggest, most common, and most remotely exploitable stuff is user error. Happens all the time. It's a big problem. We're not going to solve it necessarily, in this session, but like this is fundamentally, and users are more and more part of the problem is as we make everything on the bottom of this chain more and more secure, users fundamentally become more and more the weak link. Like just social engineering and phishing is going to be a big problem for a long time. Okay, underneath that, protocol errors. Because protocols are complicated, they're going to exist, they're going to be really big, heartbleed, these types of things. They're going to be out there, right? Then you have software bugs, right? They're pretty common. We get CVEs all the time. We have hardware bugs, meltdown specter, and then various side channel problems. And finally, there's direct readout at the bottom. And the reason why I kind of draw that as a relatively small thing is that literally you have to have the hardware in your hand to execute the attack compared to user error, protocol errors, these types of things, right? And the attack surface is literally measurable in microns in these cases. And there's actually, as you attempt to do direct read, there's a high chance you destroy the actual chip you're trying to read out. So it's like, you know, it's a threat. It's definitely a thing you should worry about if you're trying to store millions of dollars of crypto on a chip or something like this. But it's not, it shouldn't be up there with, like, necessarily all these other concerns. And perhaps more importantly, actually, when you have closed hardware, and this is kind of the crux of it, is that if you have those SEs, those secure elements, where typically today there's an NDA, you can't know anything about the hardware, you can barely know anything about the API. It runs a bunch of sort of like closed source software blogs to drive a bunch of ciphers you don't understand. What happens is your visibility into the attack surfaces gets hazy somewhere between the protocol and the software layer, right? Because, if there's a subtle bug, say in like initial value setting of some AES cipher or something like this, but you can't get through the NDA to sort of see what the underlying library looks like, it can lead to protocol errors, can lead to a whole bunch of other things. And so even though the hardware itself is under NDA, the impact actually bubbles up the layer and actually causes a lot of problems. This is why everyone is like banging the drum, like we have to get rid of those NDAs and SEs, because in order for us to even do analysis of what looks like bugs, we need to know what the lower layer looks like, right? And then, so in working with Chromium to try and build, secure element that is open, but we still have a closed PDK. Not all the RTL is fully open. We want to open as much as possible, but there are just some elements that can't be opened for a number of reasons at this point in time. So you don't necessarily get the visibility all the way down, for example, to direct readout or side channels, but you can get a reasonable amount of visibility of things like hardware bugs, because if the crypto cores are open source in RTL and there's an error in it, we can go ahead and actually analyze that in gate level simulations to try and figure out what's going on. And then that actually just makes all the other layers above it, software bugs, protocol errors, much more analytically tractable, right? We can actually find patches, workarounds, these types of things. A lot of, as long as we give ourselves enough rope to hang ourselves with, we're going to be able to patch and solve bugs a lot faster, right? So even though it's the case that like we have a closed PDK, I think there's still meaning in working on RTL level FOSS designs, right? So for example, on a kind of pros and cons slide here, nearing the end of this presentation, the pros of this approach is that we can have a reduction of software bugs because we can sort of like analyze software all the way through the APIs down to the hardware. We can actually look for the timing errors. We can run tests to actually use sort of glass box analysis of the hardware to make sure we don't have any software bugs. The more importantly is actually that it's not, there's also the problem is that there are hardware bugs. You're not going to ship perfect silicon, but when you actually have the RTL available, we can actually do analytical patching of hardware bugs. So the antithesis of this is what is going on with like the spectrum mitigations. So we have SGX, which is in all the Intel CPUs, and it's just been this agonizing striptease of there's whole research departments now who just spend their lives churning out papers about we found another timing error in the microarchitecture of Intel because it's closed, right? We can't actually analyze what it is. We think we have mitigations. And then, you just keep on sort of like agonizingly working through this cat and mouse game of countermeasure and then break and countermeasure and break, right? If you actually had the whole microarchitecture available, you could see all the state and you actually can factor that into the design of the compiler for the mitigations, you'll have a much better chance at patching out hardware bugs like that. Furthermore, we can also know if we have bad actors, if it's bug or backdoor, we can actually look at the code and say, was that what's going on based on the structure of the code? And there's going to be some improvement in physical security in that the gross morphology is constrained. If your RTL calls for a megabyte of RAM and there's 2 megabytes of RAM on the chip, there's a problem, right? So we at least we have some ability to sort of constrain the gross size of the chip. It won't protect you against people who are doing via level patching of mass or something like this to flip individual bits, but it will it prevents people from doing things like, I shipped you an SE. It's not actually an SE, it's actually an MSTU that's totally insecure, emulating your SE, but you could, it's hard to tell. The cons, of course, is that we can't be sure that the transistors match RTL. So there's always a chance that there's someone in the foundry or someone in the process, the tape out, has put something kind of tricky on the inside. There's no improvement in the analytical difficulty for side channel and direct readout vectors because you don't have the chip layout to sort of help you analyze these things. Doesn't improve the situation for transistor level inspection. And at the end of the day, there's sort of like this awful feeling that you're still standing on turtles. There's still a layer that you can't get to, right? So it does feel a little untethered and unmoored. It's not great, but I think it's better than nothing. The straw man argument against all of this, and I've had people throw this at me now, is like, if all things were equal, of course, a fully open PDK is better. If they were all equal, I agree with that statement 100%. But the straw man argument is that because security is important and reticles are huge, just make your security chip on 180 nanometer open PDK process and just use the whole damn reticle, right? You can get all the capability you want. Why do you want to go to 28 or 22 nanometer? The obvious problem is that there's physics and form factor economics assume the same RAM and ROM capacity, same microarchitecture. You've got like a 20x cost difference, going from a 16 square millimeter chip to whatever 400 square millimeter chip, right? There's also speed and power difference. There's a form factor difference. 19 by 19 chip can't fit in a smart card, for example. So there's just some barriers there. But even if you're willing to accept all of these things, the analysis isn't quite fair because not all PDKs are equal. If you actually look at today's 180 nanometer open PDKs, I've got a friend, Sean Cross, who's actually doing this right now. He's gone and taken the most recent 180 nanometer open PDK, and he did a trial layout. You can see here's a 3 by 3.5 millimeter chip. It has only 8 kilobytes of RAM. Those are on the left, and the register files take up a third of the chip on the right hand side. And normally they'd be much smaller in like a closed source version of this, but because the foundries have basically invested no effort at all into porting SRAM into it, the memory macros are essentially flip-flops that have been just tiled out, right? And so you're not even close to the memory density that you're hoping to get for the analysis to be equal. They're working on it. It's not that it's impossible to climb that hill. It's just that we're really actually not. It's not as simple as saying like, oh, because the thing that people will say is like, well, Pentium's taped at 130 nanometer and they run at like 2 gigahertz and they had all this memory on the side. Why can't you do this, right? Like, why are you even bothering these sorts of things? Because Intel did it at 130. We're not Intel, right? We don't have the resource. We don't have the PDK. There's still a lot of work to go on that. So you can't necessarily compare those two apple to apples. And then there's just opportunity costs, right? So, outside of the field of security research, security is actually considered more of a barrier to adoption. Like if you put too much security around access to a bank or a website, people don't sign up, right? And so it's hard to actually upsell security as a feature. Consumers regrettably don't want to pay more for it. So if you say, I will offer you this secure token for $200 instead of like $10 or something like this, and you say, but it's open source and it's an open PDK, they'd be like, no thanks, I'll go with the cheaper one, right? It's just, that's the reality, unfortunately. And then security tends to set our own standards. There's an old saying, don't roll your own. I mean, and first movers have the ability to set de facto standards. I presume that's one of the things that this forum is trying to do, is to try and be a first mover and set de facto standards around whatever they want to do. And if you if you as an open source community ignore the standards process and just allow ARM and proprietary technology to become entrenched later on, once you have the open PDK, all the sort of stuff, you're going to have a much harder time getting full open technology into the whole stack. And the microarchitectural lock-in is real. I mean, x86 versus every single other architecture won because of code compatibility, binary compatibility. And so one of the things that one of the reasons that I got very, I felt it was important to engage with Cranium, even though they're working on a closed PDK, is that the original plan called for an ARM CPU only, and if that was just essentially became the standard for all secure elements and for cryptocurrency, at the end of the day, you're going to end up with a huge base of code that runs ARM shipped on millions of devices. And then finally, when RISC-V gets around to getting its act together and we have the open PDKs and stuff, you're gonna have to climb up this, multi-million installed user base and developer hill to go ahead and replace it, right? So ideally, we start early and we can get at the ground level and have openness baked in as far as we can. So at the end of the day, which is better, like bottom up approach or top down approach? I say por qué no los dos, right? I mean, like this, I think the people who say that it's a mistake to be working on a top down approach without worrying about the PDK is missing the point here. There's people who are working on the PDK and there are people working on getting the full open to the transistor level, and they're doing a great job of it. I don't think we all have to be playing on one side of the field. It's okay to go zone. And so, I think it's important to also think about from the top down and try to make sure that we have, at the RTL level, at the architecture level, at the software level, that we have all the open gates open, so that by the time when the open source PDKs arrive, we can actually have a full open stack ready to go without having to then work our way up the chain. So that's it.